we have here for chapter 4 is atomic mass. So we've been talking about the atomic mass on the periodic table. Now we're going to figure out where it comes from. So because isotopes have different masses, but they're still atoms of the same element, we can't just say the mass of one isotope and assume it represents all of that of the entire element when we're talking about atomic mass, right? I want to be able to talk about the atomic mass of all atoms of one type of element, for example. So we need to include information about all of those different isotopes to properly represent the atomic mass of an element. And so we use an averaged mass based upon the naturally occurring abundance of the isotopes of the element. So atomic mass is actually an average mass of an element based on the percent abundance of the naturally occurring isotopes of that element. So basically it's a weighted average is what you might think about it. You know, when you're calculating your grades for class and your professor says, you know, this is worth this much of your grade, this is worth that much of your grade, same kind of deal here. We're saying, you know, if it's got the highest percent of abundance, well then we want it to count more towards our mass. If it's got a smaller percent abundance, we want it to count less towards our mass, basically. Atomic mass is going to be the fraction of atoms that exist as that isotope times the mass of that isotope, and then you add them all up together. It's kind of confusing the way it's written out there. So we're going to go ahead and work through some examples here. So example 1 states that magnesium has 3 naturally occurring isotopes as follows. They're listed here in the table, and then we're going to use this information to figure out the atomic mass of magnesium. So I'm going to go ahead, I'm going to go to the lab so that I can use a whiteboard, and I will clue you back in when we're ready to do some math. Okay, so I am here in the lab ready to work through example number 1. So example number 1 says magnesium has 3 isotopes. It gives this information about the isotopes, and we want to know what the atomic mass is of magnesium. So we're going to go ahead, we're going to set this math problem up and do some calculating. So again, basically we're just taking weighted averages in this case. So our atomic mass is going to take each of these into consideration with their percent abundance. So I might write it like 78.99% times 23.99 AMU. To that, I am going to add 10.00% times 24.99 AMU. And then I have a third isotope that has 11.01% of the abundance, and it has 25.98 AMU for the mass. So again, basically this is just taking a weighted average. It says basically that, you know, almost 80% of your information comes from here, 10% comes from here, and 11% basically comes from here. That's kind of the idea. However, we know that we can't actually work with percentages in math problems, so we need to convert those to decimals. So I have atomic mass is 0.7899. Remember, to convert a percent to a decimal, we just divide by 100. So that's 23.99 AMU. So 0.7899 times 23.99 AMU. To that, we are going to add 0.1000, 24 times 24.99 AMU. And then I'm going to divide 11.01 by 100, 0.1101. And I'm going to multiply that by its mass, 25.98 AMU. So that's what I got worked out. Now to find the atomic mass, I'm just going to add all those numbers up. So if I'm looking at my significant figures here, when I do this multiplication problem, I have 4 sig figs here, 4 sig figs here, so I should have 4 sig figs in each of these cases. based upon the information here, and then I round to the correct number of decimal points when I'm done, so I know my answer has the proper number of sig figs. So I'm going to go ahead and multiply this out in my calculator. 0.7899 times 23.99 plus 0.1000 times 24.99 plus 0.1101 times 25.98. Well, that's going to be 24.309. I'm going to round to 2 spots after the decimal place because that's what my answer is going to have here. So 2 spots after the decimal place for sig figs in this case is 24.31 AMU. So 24.31 AMU is our answer. So that would be the atomic mass for magnesium. Again, atomic mass is basically taking these weighted averages. I'm just going to take my percentage, multiply it by my mass. However, we can't just multiply those two numbers directly. We can't use percentages directly. We have to divide them by 100, convert them to a decimal, or what the book calls fraction, so decimal or fraction here. So I convert to my decimal number, and then I can multiply by my masses, add them all up. Bob's your uncle. There's your answer. So the atomic mass in this case is going to be 24.31 AMU for magnesium. Another example here as well. It's going to be relatively close to the first one in concept. So here we have boron is a naturally occurring isotope with two different boron has two naturally occurring isotopes, So boron has two naturally occurring isotopes as follows. And now we're going to go ahead and find the atomic mass of boron. Okay, so I've gone ahead and written example 2 up here on the board, just a quick summary of what we're doing. It says that boron has 2 isotopes with this piece of information about each isotope. What is the atomic mass? So we're going to go ahead, run through, and calculate the atomic mass again. This is basically the information we're given, and we're going to atomic mass. So again, I'm just going to go through, kind of take that weighted average, and figure out what we got going on. So I know atomic mass is going to be each of them taking into consider their percent abundance added together. So I might have 20.0% times 10.0 AMU plus 80.0% times 11.0 AMU. So this is the math that we got going on. We know 20% of our atoms have that 10 AMU mass and 80% have the 11.0 mass. So to do percentages, we always have to convert them to the decimals before we can actually do some math with them. So if I wanted to do math with them, I would divide by 100. So now I have 0.200 times 10.0 AMU plus 0.800, remember I'm just dividing by 100, times 11.0 AMU. So now that I'm not working with percentages, I can actually work through this problem here. I can multiply these two numbers together and then add to figure out what my atomic mass is. So I'm going to go ahead and type that in my calculator. So the number that I get in my calculator is 10.8. And that'll be AMU. So that's our average mass there. We can see that it's much closer to the 11. We're taking like 80% of 11. So 80% of our atoms have a mass of 11. So that means our atomic mass is going to be much closer to whichever isotope has that larger percent abundance. So in this case, we have 10.8 AMU. I know I have the right significant figures because each of these numbers has 3 sig figs. Each of these numbers have 3 sig figs. And then when I add them together, they each only end up with 1 decimal place. So boom, 10.8 AMU is our mass. We're going to go ahead and work through example number 3 here. So the idea here is I've got some made up element. So I want you to recognize that when I'm talking about elements, I'm always going to be giving you real life examples of how those things work with that specific element. However, if I make something up, I'm always going to call it a made up element, so you know that there's not really an element that fits these specifications. So suppose I have a made up element and it has 2 different isotopes. So on my screen, I have one isotope with a percent abundance of 90 and one with a percent abundance of 10. So if I'm thinking about this, I'm going to keep that in my head. The question is asking, what can I determine about the relative size of the atomic mass? So I can kind of sort of qualitatively, really kind of like touchy-feely think about, figure out what my atomic mass might average to based upon how we calculate the average without actually having to do any math here. So this might be a way you might check yourself. Did I get the correct percent abundant or the correct percent atomic mass based upon which one of my isotopes is more abundant? So what can we determine about the relative size of the atomic mass? Go ahead and pause and then come back for my thought process here. Resume. So in this case, if we're thinking about the fact that we have one isotope with an atomic mass of 78, or with mass of 78 AMU, that has a percent abundance of 90. So most atoms of my made-up element are going to have that mass of 78 AMU. 9 out of 10 is what 90% means. So 9 times out of 10, when I grab a atom out of my bag, it's going to be that 78.00 AMU mass. However, 1 in 10 times, that percent abundance that's represented by 10%, for the 80.00 AMU mass, it's only going to occur less often. So when I'm thinking about the fact that my atomic mass is a weighted percentage, I know that most of my atoms are going to have that atomic mass or have that mass of 78. So if most of my atoms have a mass of 78, that means that my atomic mass, my averaged mass, is going to be way closer to that 78 than it is to that 80, because I'm taking into consideration that 9 times out of 10, I have that 78.00 AMU when I'm doing that atomic mass calculation. When we look at the equation as it's written here, see, we're taking into consideration those fractions, those parts of a that ratio of how they are occurring naturally. So when I'm thinking about this, that means that my atomic mass is going to be much closer to 78 because most of my atoms have that mass of 78. So I can conclude that if I'm thinking about just that relative size, I could say I know my atomic mass would be closer to 78.00 AMU than it would be to the 80 because that isotope is more abundant. And then we'll go ahead and work through number 4 as well. So number 4 is saying, again, I've got a made-up element with 2 isotopes. One has a mass of 25.00 AMU, and the other has a mass of 28.00 AMU. And the calculated atomic mass that I get is 25.36 AMU. I'm trying to determine which isotope is more abundant. Which one is more abundant? Go ahead and pause, think it through yourself, and resume to see which isotope is more abundant. So in this case, we're thinking about the fact that we have 2 different isotopes. We want to know which one's more abundant. Well, I can take some information from that clue of our atomic mass being closer to one than it is to the other. 25.36 AMU is very, very close to 25.00 AMU. So we can assume that one's more abundant. It's skewing that average closer to it. Therefore, it's more abundant. Whichever one the atomic mass is closer to, if I have 2 isotopes, is more abundant. pretty straightforward, but it takes just a little bit of thought. So those are our problems working through atomic mass, and that's chapter